That's right. That's right.
Oh wait, I did. Yeah, I had a one of those like.
Okay. Yeah. What's up? Probably not. I don't know.
We should just.
All right. You can watch Star Wars any day of the year because you're in America and you're lucky ducks. So that's the way it goes. Happy May the 4th. Let's get on with the show. Today, we're going to finish up our discussion on molecular formulas from empirical formulas and just start talking about chemical reactions. We're finally going to get to do some chemical reactions. So that will be fun, and it's a really fun lab. It has a lot of little reactions to do. So hopefully you will enjoy that as I enjoy it every year. Everybody turned in their lab on percent composition. And if you are at home, you're supposed to turn it in to the classroom. Okay. And in your classwork feed, there was the note sheet from yesterday. We're going to go and do a little review because it seems like people don't remember. Oops, I better turn this off so it doesn't make noise. And let's start. Well, I won't pick on Logan because you weren't here yesterday. Or you were here. You were distant, right? Do you have your Chromebook?
I was sick, so I wasn't.
You weren't really focusing? Okay. So if you don't have your Chromebook, you should have a piece of paper and pencil to take notes on it. And it's probably a good idea to have a paper and pencil anyway. Mr. Burt Whistle, tell us what empirical formula is.
Shows the smallest whole number ratio of the atoms of each element in the compound.
Beautiful. Smallest whole number ratio of the atoms of each element in a compound. Sometimes, so we've got empirical and we've got molecular. So again, it's molecular because these are always happening with covalently bonded compounds. So they form true molecules. Ionic compounds are always in empirical form, simplest whole number ratio. So yesterday we looked at an example with nitrogen and oxygen. The nitrogen came out to be 1 and the oxygen came out to be 2.5. You can't have 2.5, thank you, of an oxygen. Okay. Oh. I'm glad you missed. All right, so this can't happen. We use these numbers, these proportions for subscripts, and you cannot have 2.5 oxygen atoms. You can only have whole. So in order to make this into the molecular form, we have to double it, okay? And if we do that, then it becomes N2O5. Okay, if we double one, we have to double the other one to get them to go to whole numbers. Sometimes you can round, not very often, right? First step in finding an empirical formula is what, Julian? Changing percents to grams. So lots of times we do analysis in the laboratory and we find out the percent composition. From percent, we make believe that's a perfect 100-gram sample. Once you got grams, what are you going to do with the grams? Lauren? Absolutely. And so you have to have each of the elements listed out, whatever their mass is, divide by the molar mass to get moles. That may not come out to be whole numbers. So, well, it won't come out to be whole numbers. So Bethany, what's the next thing we're going to do?
Divide the number of moles by each element by the smallest number of moles.
Find the smallest one, divide it into everybody. So at least one of the elements is going to come out with a subscript of 1 or a proportion of 1. Divide by the smallest number of moles. And then sometimes that takes care of it. Sometimes it doesn't. So the next thing you have to do, Amani. Perfect, round or multiply to get all the ratios to whole numbers. Okay. What do we do with those whole numbers, Aiden? Step number 5. Anybody help him out? The whole numbers become the subscripts. And that's our formula. So that gives us a count of how many atoms of each element should be in the simplest form. And remember, proportions, there's compounds that are multiples of the empirical formula. So that's where we're jumping in with molecular formula and our notes. So that was just a review of yesterday's stuff because it's kind of weird, I think. Any questions in the classroom? Any questions from the home peeps? We have not done the molecular formula yet. Okay, I got Isabella, I got Anthony. Marlene, I don't see Sarah E. I see Tony. Oh, I see Joshua. And no Katerina. Okay. Beautiful. Here we go with a little bit on molecular formula. Where are you? There you are. So molecular formula is the formula of the real molecule. Sometimes they're the same. Sometimes it's a multiple. Okay. Occasionally, like water, H2O. Okay. The proportion of hydrogen to oxygen, 2 hydrogens for every 1 oxygen. Turns out a water molecule is 2 hydrogen atoms and 1 oxygen atom. End of story. There are things like the stuff we were looking at yesterday where there's the same elements, but sometimes they're the simplest, 1 to 2 to 1, and sometimes there are multiples. Okay. So how do we get that figured out is what we're going to learn today. All right. So again, the molecular formula is the formula of the real molecule with the actual body count of all the atoms in that compound. And again, sometimes they're equal. Those are the nice ones. Okay. But of course, when we're learning about it, they're not going to be. Okay. So the simplest way to do this is to realize that this will always be the lowest number. Always be the lowest mass for the empirical. And the molecular is either going to be equal to it or multiple of it. Okay. All right. So, and it's going to be a simple, it's going to be double or triple or fourple or 5 times or whatever. Okay. I like saying fourple. Okay. So did we look at ethine and styrene yesterday? Did we get this far? Anybody remember?
Yeah.
Okay. No, yes, no. Okay. So ethine is commonly called acetylene by most people. Proper chemistry name is ethine, 2 carbons, triple bonded. Styrene, which most of us call styrofoam when it's poofed up as the polymer, has 8 carbons with 8 hydrogens. Both of them have the same empirical formula, which is what? 2 to 2.
1 to 1.
And 8 to 8 is 1 to 1. Okay. So their empirical formula is identical. Their molecules are not, as you could see from their structure, which you don't have any way of knowing how to figure that out yet. It's okay. So empirically, it's 1 carbon for 1 hydrogen. Molecular, it's double, or I don't know what 8 times octuple. I don't know. So, and the molecule could be, and it could be 6 times. There's benzene that's 6. There's all different ways to get the same 1-to-1 ratio for these, okay? But their molecular mass is different. All right, so first step, calculate the empirical formula's mass. So the very first step is how much should 1-to-1 be, or 1-to-2, or whatever it is you're dealing with. So 1 carbon, 12.0, 1 hydrogen, 1.0. You can throw the ones on there, 13.02. If that was the molecule, just 1 carbon with 1 hydrogen, which it never will be anyway, it should weigh 13 grams per mole. Turns out acetylene is 26 grams per mole. Turns out, and again, you don't have any way of knowing this, but you would have to be told, and that's a really important piece. The styrene is 114 grams per mole. So I'm going to tell you that this one, the empirical mass, you calculate. These, the molecular masses, you have to be given. Okay. Right. So you're going to be told that upon analysis, the real molecule weighs such and such. You're going to compare that with what you found and what you did over, what you get over here. So you divide by the smallest. You divide by the empirical into the molar mass, and that will give you the multiplier that you need to do to the understood subscripts in your empirical formula. And of course, it's always better to do examples. So let's go through an example and see if it makes sense. Give me a second to finish typing. Flying fingers. I hate flying fingers. Okay to go? Nope. Okay, you can look at the recording after we're done if you need to. It's also in the book, believe it or not. So we looked at these 3 compounds at the beginning of this discussion: methanol, ethanoic acid, and glucose. All of them have the same empirical formula, but they don't have the same molecular formula. They all have the same 3 elements, but in different multiples. So empirically, they're all CH2O, 1 carbon, 2 hydrogens, 1 oxygen. One of them, methanol, actually is the same molecule formula. If you do this, 1 times 12, 2 times 1, 1 times 16, and add them up, 2 times 1 is 2, 14 makes 30 grams per mole. And methanol actually has a molar mass of 30 grams per mole, but ethanoic acid doesn't and glucose doesn't. But they're a multiple of this. So they threw in these other examples, ethine, which is what we're just looking at, and benzene. I don't know why they didn't use styrene like they did in the pictures. But if you took 26 divided by 13, you get 2. So instead of 1 and 1, the subscripts become 2 and 2. If you take 78 and divide it by 13, you get 6. So instead of 1 to 1, you get 6 to 6. It's still equal numbers of particles. On these, okay, ethanoic acid is 60 grams per mole. One of them is 30, one of them is 60, and one of them is 180. You have to be told that, okay? You're not going to know that off the top of your head. And so what you do is you do 30 divided by 30, you get 1. 60 divided by 30, you get 2. 180 divided by 30, you get 6. And so this empirical formula is the actual formula for methanol. Twice it is the formula for ethanoic acid. 6 times is the formula for glucose. Okay, so it's weird stuff and weird words. What's empirical mean again? What's it mean? E for empirical and experimental. Elephant, E for elephant. Okay, so let's try one, all right? So here's our, and I don't know why it's 60 again. I have no idea. It just happened, okay? So here's our example. Let's try it. We got ourselves some compound. The actual molecular mass is 60.0 grams per mole. Okay, molar mass of the molecule, of the real compound. You've already done the percent composition, changed in the empirical formula. The empirical formula is CH4N. Step number 1, find the molar mass of the empirical formula. 1 carbon, 4 hydrogens, 1 nitrogen. Okay, that's step number 1. Absolutely. Well, some of you might be able to do it in your head. These aren't too bad. This one's not too bad. It's late. It's gonna be weird when we go back to going to school until 3, huh?
Yeah. It's gonna feel like a long day.
You got that one straight.
We're not going back till next year though, Mom.
That is correct.
I'm not even gonna be trying to
So carbon is what? How many grams per mole for carbon? Come on, you guys should know that by now.
12.0.
Okay. How many grams per mole for hydrogen? Good job. How many grams per mole for nitrogen? 14.079 or 08, right? Is that right? 01? On this one, it says 14.007. So 14.01. Okay, it's 007, sorry. So this means that this is 4 here. So I'm just going to switch it right now so I don't forget. So 12 and 4 and 14, 30. And if you want to keep to the hundredths place, that's great. That's the empirical formula, molecular mass. If the real molecule had just 1 carbon, 4 hydrogens, and 1 nitrogen, it should weigh this. I was having fun, sorry. It's getting so boring. So, everybody good so far? Okay, step number 2 is you're going to take the real molecule's mass and divide it by the empirical formula mass. And all of you should get 2. It'll be 1.996 or something like that if you go to the hundredths place. It's 2. That's a legitimate place to round, right? And they're selling you something for $1.99. It's $2. Okay, silly. All right. Now, what do we do with that 2? Multiply the subscripts. In the empirical formula. All right, so instead of a 1 carbon, we'll have a 2 carbons. Instead of 4 hydrogens, we'll have 8. Instead of 1 nitrogen, we'll have 2. So the real molecule is big. It will only ever be equal or bigger than the empirical formula. So 1 to 4 to 1 is the same proportions as 2 to 8 to 2. Okay. So proportionality doesn't change, just that it's a multiple of it. Questions?
We have another example.
That's it for examples today. Keep your clothes on, please. Yep. And that is it for today. So tomorrow, one of the things that you'll get is an example starting you from start, percent composition to molecular formula. Okay. And then there'll be a short video too. That's my plan right now, subject to change, but that's my plan. Any questions from home peeps?
Oh, I didn't learn.
You should do that. I probably will remember that you're here, but just for the sake of argument. Okay, the next thing, we're going to put that away. The next thing you're going to do is please find this note sheet. Questions yet?
Did we check in the lab?
Yes. The next thing we're going to do is start talking about chemical reactions. So we're going to start doing some real chemistry finally. And the first thing I want to start with, because this is the picture at, well, there's a story about this on the start of chapter 11, is about the Hindenburg. So who knows about the Hindenburg? The blimp, yeah, the dirigible, the Zeppelin, the airship that went kablooey. And it's pretty sad. And then we'll just barely also learn about Mr. Remsen. So Ira Remsen was an American chemist, and we'll find out about him later. And that will need to be turned in before you leave today. So, but let's look at the Hindenburg first. Pretty tragic.
This is the airship Hindenburg, burning up while trying to land in New Jersey in 1937. 97 people were trapped inside. It was a big deal at the time. The Hindenburg was the greatest passenger airship ever built. Imagine something the size of an ocean liner, but in the air. And it could make the journey from Europe to the US in half the time. It was a shining example of the future of commercial air travel. And all it took was a spark to bring the whole thing down. Air travel was on everyone's minds in the early 20th century. Aviators like Charles Lindbergh and Amelia Earhart became huge celebrities after they conquered the Atlantic in airplanes. But airships were something else entirely. Just 2 years after Lindbergh famously crossed the Atlantic in a cramped monoplane, a giant German Zeppelin flew around the world, carrying paid passengers who ate comfortably in a full-service dining room and slept in private berths.
Airships could do things that airplanes couldn't even imagine doing in the late 1920s, and people were really, really wrapped up in that. They thought it was kind of miraculous, and they thought it was the future.
And in 1936, the biggest and grandest airship yet was built, the German LZ-129, named the Hindenburg.
There she is, a fine example of simplicity and economy of design, a triumph of lighter-than aircraft, the like of which the world has never seen before.
It was a monstrous feat of engineering and a symbol of Germany's rising prominence in the early years of the Nazi Party.
The world's greatest lighter-than-air ship, the Hindenburg, that superliner of the sky, made her first trip to America from Germany in March 1936.
That year, the Hindenburg made 17 intercontinental round trips carrying passengers. It had a dining room too, and a reading room, and a separate lounge. It even had a smoking room, a separately ventilated space where passengers could smoke under the supervision of the maitre d', who held the only lighter. Which brings us to a very important element in this story: hydrogen. Hydrogen gas is lighter than air, and people had used it for centuries to lift aircraft like hot air balloons. It's highly flammable, but cheap and easy to make, as opposed to its safer, non-flammable cousin, helium. But the United States,
So I have to qualify something from this movie. He said hot air balloons. You would not have a heater with hydrogen. It would go kablooey. Okay, so nowadays we use hot air balloons because we're heating up atmospheric gases. So back in the 1600s, there was a pair of brothers in France called the Montgolfier brothers, and they're the first ones to do serious ballooning. They stitched together animal bladders, cow bladders and sheep bladders and stuff like that to make their balloons nice and stretchable, right? And then they pour acid on the metal and make hydrogen gas and fill up these balloons. And they went flying out over the fields around Paris where the peasants were out there, grazing food, and it freaked them out because they had no idea what was going on. And so when the balloon came crashing down, they went chasing after the Montgolfier brothers with their pitchforks. It's pretty funny. Lots of balloonists between the 1600s and the early 1900s, but it was originally hydrogen, and they blew up too. I think one of the brothers died, the other one continued on. But helium doesn't blow up. That's what's in birthday balloons, right? But we have pockets of that here in the United States, but they haven't discovered it other places, and we kept ours. And it's really important. It's really such an important element. It shouldn't be in birthday balloons, but anyway.
But the United States, who at this time produced the rare gas almost exclusively, embargoed its sale in 1925. Countries around the world developing lighter-than-air programs had to rely on hydrogen, and their airships were blowing up. In the US, the hydrogen-powered Roma exploded and killed 34 in 1922. In 1923, the French Navy airship Dixmude did too, 52 dead. And in 1930, the UK ship R101 went down, 48 dead. But the Germans weren't worried. By the time the Hindenburg embarked on its first North American flight of 1937, not a single German passenger airship had crashed.
They were very confident that, yes, this is a dangerous, highly flammable gas. We know that. But if you take the right precautions, you can control the risk.
On May 6, 1937, that's not what they did. The ship was 12 hours late. And what's worse, the crew had good reason to believe it was leaking hydrogen. The back end was dipping toward the ground, and they couldn't properly balance the ship.
For 3 hours, the dirigible circled the landing field at Lakehurst, New Jersey, dumping more water ballast than ever before in vain efforts to level off.
Plus, the air was charged with electrostatic activity due to a recent thunderstorm, and another one was on the way. That means they were trying to quickly land an enormous hydrogen-filled airship in electrically charged conditions that was likely leaking flammable gas. And, well... When Hindenburg caught fire, a crew of reporters gathered for a routine photo op sprung into action. Photojournalist Sam Shear only had time for a single exposure, but of all the press photos taken that day, it's this one that's most remembered. It somehow manages to perfectly frame the entire disaster. The panicked crowd running in view of newsreel cameras, with the hastily dumped water ballast still visible in the background. The name Hindenburg barely illuminated by the bright flames lighting up the entire top of the ship. And the faulty tail, now completely engulfed, just moments before the flames burst out of the nose and brought the ship crashing to the ground. The image of the Hindenburg burning was unlike anything people had seen before, a disaster photographed as it was taking place. In the end, out of 97 people on board, 35 plus one crewman on the ground died. That means that about 2/3 of the people inside of that actually escaped. But the numbers didn't matter. Hydrogen airships never flew paid passengers again after that day. The Hindenburg wasn't the first or even the deadliest passenger airship disaster. It was just the one that was caught on film, and that's why it was the last.
So we take taking pictures for granted, but there's a lot of picture taking and videos that are helping to change things even today, as we know. So no more dirigibles filled with hydrogen. Of course, there still are blimps, right? But now they're filled with helium, and there's only the Goodyear blimp. I think there's only a couple of them. Because helium is really valuable for scientific research. It helps cool things down. You need to do that for like the super colliders and stuff, and for medical instrumentation, for imaging. So yeah, don't worry if you see the Goodyear blimp going overhead. It's not going to blow up on you. So I just wanted to share that. No chemistry class would be complete without that giant experiment going off tragically. We're going to learn about what chemical equations are, how you set them up, how to balance them, all that kind of stuff. But to start off with, we're going to find out about a gentleman named Ira Rumson. And on this document is a lovely picture of him with his beautiful sideburns. He was, I guess he probably was still alive when the Hindenburg crashed, 37 was when the Hindenburg, so he died before that. But the cool thing with Rumson is he's an American chemist, American scientist. He got his MD, his medical doctor's degree, and practiced medicine, but not for long. He went off to Europe to go get a PhD in chemistry, crazy fool. So he eventually came back to the United States and started the chemistry department at Johns Hopkins University, which you probably have heard of over the last few months many times because they are extremely reputable, and they are maintaining, they're usually cited when we hear about COVID numbers. So Rumson, how did he get interested in chemistry? Why did he want to do chemistry instead of medicine? Well, it started, this is a clip from his biography, if you will. I don't know if it's autobiography or a regular biography. But it starts with, while reading a textbook of chemistry, I came across the statement, nitric acid acts upon copper. And so he wanted to find out what that meant. This video is by a professor somewhere, Melissa Rathier. I've done it before in the fume hood, but it's really it's a hard deal for me to videotape it for you, for the distance peeps. So I thought I'd just play hers. I'll show you a picture of my setup on Thursday. But on your document, there's observation data table. So before, during, and after. Most people focus on the middle part, what's going on when it's reacting, but it's really important to know what it looked like to begin with and what it looks like when it's all done. So I want you to have that open, but to watch this. And so this is her setup. She's got a beaker with pink liquid in it, an Erlenmeyer flask with a hose into the pink liquid. And then this, you will find out, is the nitric acid in a graduated cylinder. So what's in the pink liquid? Well, it turns out there are lots of indicators. And one very common one for doing acid-base and checking for neutralization is called phenolphthalein. This really crazy word, phenolphthalein. It, oddly, is pink in a base. Okay, and so basic solutions, those with high pH values like sodium hydroxide, will turn pink. Now, we expect pink litmus paper to indicate an acid, right? Red or pink for acid. This is the reverse. It turns out it's clear or colorless when it's in an acid. Okay, so once the solution goes acidic, the color goes away. On the other side, like I said, is the Erlenmeyer flask, and you can barely make out at the bottom if you look really closely, if you know what you're looking for. There's a penny in there, so a copper penny. And I'll let her talk.
Rumson demonstration. What you're going to see here today is the Rumson demonstration, and I'll start by reading an excerpt from Rumson's biography. This is him describing an experiment that he first performed at the age of 12. It says, while reading a textbook of chemistry, I came upon the statement, nitric acid acts upon copper. I was tired of reading such absurd stuff, and I determined to see what this meant. Having nitric acid and copper, I had only to learn what the words act upon meant. Then the statement, nitric acid acts upon copper, would be something more than mere words. In the interest of knowledge, I was even willing to sacrifice one of the few copper cents then in my possession. I put one of them on the table, opened the bottle, marked nitric acid, poured some of the liquid on the copper, and prepared to make an observation. In this setup, you see that on the right-hand side, we have some copper in the Erlenmeyer flask, and this will mimic Remsen's experiment. We'll also modify it by looking further into the reaction, and on the left-hand side, you can see that we have a beaker with a pink-colored solution, and it contains base, sodium hydroxide, and phenolphthalein. I'm now going to add the nitric acid.
What's that? The copper's in the Erlenmeyer flask, yeah. So if you watch it over her shoulder there, you can see it looks like water, but it's not. And she turned on the fume hood. All right, so pretty quickly, it starts turning a brown gas, generating a brown gas. The liquid goes from clear to green, and there's bubbles happening on the left as the gas is getting pushed out. It gets really hot also.
While observing the reaction, it's important to look at both the right-hand side and the left-hand side and note any changes. This reaction also models the production of acid rain. The brown gas, which is a nitrogen dioxide gas, when it comes
So look at the left-hand side, it's not as pink anymore.
into contact with water, will produce an acid. And so as you can see on the left-hand side, the base that was previously there is neutralized.
So now it's clear.
The brown gas is one of the emissions from our cars.
So it's actually the emissions from your car reacting with the oxygen to make nitrogen dioxide, but that's okay. Notice now the brown gas is in the hose, it's into the water, percolating it in there.
We strive with new vehicles to remove from the emissions. While you continue to observe, I'll read Remsen's comments after doing the experiment. But what was this wonderful thing which I beheld? The scent was already changed, and it was no small change either. A greenish blue liquid foamed and fumed over the scent and over the table. The air in the neighborhood of the performance became colored dark red. A great colored cloud arose. This was disagreeable and suffocating. How should I stop this? I tried to get rid of the objectionable mess by picking it up and throwing it out the window, which I had meanwhile opened. I learned another fact. Nitric acid not only acts upon copper, but it acts upon fingers. The pain led to another unpremeditated experiment. I drew my fingers across my trousers, and another fact was discovered. Nitric acid acts upon trousers. Taking everything into consideration, that was the most impressive experiment, and relatively probably the most costly experiment I have ever performed.
Okay, so I'm going to speed it up here just a little bit. So it's mostly done in the flask, and there's not really bubbles happening on the left anymore. What ends up happening is that it starts to cool off, and as the gas cools off, it contracts, and as it contracts, that drops the pressure, and that's going to create a suction tube. So it's just like a straw, and as you observe it going on, you can see the clear liquids coming up in the straw. You can still see the brown in there. Clear liquid, almost to the flask, and then it whoops, I overdid it. Then it drops in.
Note in the Erlenmeyer flask.
So the liquid becomes a blue color. When I've done it before, it comes a bright blue. This is a very faint blue. I don't know if that's just lighting or concentration. And the gas is basically dissolved. There's still a little bit in there. So that's the after part. So the clear liquid's back in the flask and it's a blue color. Don't spend any more time on it. Whatever you got written, just hit submit. We'll call it good. Have a wonderful rest of your Tuesday. And I look forward to doing chemical reactions with you. Thank you. Have a great day. Thank you, too. Bye.